What if I could ride a light wave? If you could shrink yourself to become a tiny surfer that could ride a light wave, how many waves of red light could you catch in an hour? So light travels pretty quick. It travels at a rate of 3.00 times 10 to the 8th meters per second, or 1.08 times 10 to the 12th meters per hour. And for numbers you may be more familiar with, that's 670 million miles per hour. It's real fast. So the light wave we're going to be trying to catch on our surfboard is pretty quick. It's going to be hard to stay up, I have a feeling. It's also helpful to note that the distance between two crests of red light is only going to be 400 nanometers. So we're going to try to ride the light on top of a laser pointer. So we're going to shrink us down. So let's say we've got our surfer here, and he is on the top of a light wave. And he's curious, how many of these is he going to have to ride if he's trying to stay on his surfboard? I guess he's trying to stay on for just a second. We know it's going to be going pretty fast, so he's going to go whee! So how fast is it going while he's doing this? Let's do some calculations to see. So our speedy boy, he can take one wave for every 400 nanometers that's traveled. So he's wondering, okay, if there's one wave per 400 nanometers, how many waves am I going to get in a whole hour if I'm trying to ride on this? Well, we know his speed in meters per hour, so we can't be working with this nanometer stuff. So let's do a conversion. So we have 10 to the 9th nanometers, and we have 1 meter. From there, we also know that we need to get from the fact that for every 1.08 times 10 to the 12th meters that he's going to travel, it's going to take, that's how far he can go, or the light wave can go in 1 hour. So the idea is we're treating him like he's stationary, because that's what it does if he's a good surfer right here, and the light's just passed him by. We're seeing how fast that'll go. So our nanometers will cancel, our meters will cancel, and we'll be left with hours. So if we do that calculation, we will get that he would be able to ride 2.70 times 10 to the 18th waves. That's waves has a V in it. Waves per hour. So our surfer, if he's able to stay on the light wave and not crash and burn, he would be able to travel 2.70 times 10 to the 18th waves in his 1 hour. I have a feeling if he's trying to ride water waves, he would not get that many water waves in an entire lifetime. So if you have the chance, riding tiny light waves sounds like a good way to catch lots and lots of waves. Let's introduce some ideas on light now. So light, we're going to talk about its wave nature in this course. So when we talk about light waves, note that they're also sometimes called electromagnetic radiation. These are not two different things. They're the same. And electromagnetic radiation, which sometimes when you're reading, especially in your physics text in the future, if you take physics, or if you're reading on the internet, will sometimes be abbreviated with the letters EM. And that includes a variety of waves that have different amounts of energy, and has to do with some different properties of them about which ones they are. We've got things like radio waves, microwaves, infrared waves, visible light, ultraviolet light, X-rays, and gamma rays. So as a chemist, when I'm talking about light, I don't just mean visible light. If I'm just talking about light in general, all of these are different types of light waves, even if some of them, like a radio wave, might not sound like it at first. An important property of these waves, and one of the things that keeps them all connected together, is they're going to move the same speed through a vacuum. And that speed in a vacuum is 3.00 times 10 to the 8th meters per second. We will sometimes represent this with the variable c to represent it in equations. Now, as an aside, light does travel different speeds when it's going through different materials. In most problems that we work with, though, we're going to worry about how would it travel through a vacuum. We're not dealing with, what if the light is going through a different medium. But just to mention that in case you're looking at other sources, why is it they even use a variable c if it's constant? Why not just put the number in? That's because the speed of light can change if you're going through a different medium and you're having to worry about that. So, light is also, since it's a wave, we're going to discuss some definitions of the parts of the wave. So the next slide is going to be about those definitions and to review them or cover them if you haven't heard them before. I also want to make a note about the wave nature of light. In this section, I'm going to be focusing on wave behavior. However, we know experimentally that light can have both wave and particle-like behaviors based on how it's interacted with. Your text will also go into some detail with this. And this is called the wave-particle duality because light can demonstrate both properties of being a wave and of being a particle. And so now and in the next section, we're going to cover some more things about the properties of lights and start doing some calculations with them.